Welcome to the National Seminar on Polymeric, Smart, and Nanomaterials Technology, Concept, and Future Applications. Sponsored by Dr. APJ, AKTU. Organized by Central Institute of Plastics Engineering and Technology, CPET Lucknow, IPP. The objective of the seminar is to acquaint the academic and industrial world with the emerging trends, applications of these materials in various fields. So, in continuation to this, we are going to touch some portion of the seminar theme in this video.
Polymers are touching our everyday lives. Do you know what all these polymer products have in common? They all share the same origin.
So now we have the technology that is shrinking the world rapidly and allowing us the usage of materials in terms of few nanometers, the nanomaterials. These are like a double-edged sword, one of which allows us to use their materials in such a way that opens the numerous channels to the humanity, but the other side is not so simple because the size of the particles are so small that makes them very difficult to operate, just like material. Vanto black, darkest material on the planet Earth, made of vertical aligned carbon nanotubes, as we'll see in the upcoming video.
It is so black, it looks like a mistake.
All these things might look black, and we might even call them black, but they're not actually true black. But this is closer to true black than anything else on the planet, and it's revolutionizing everything from space exploration to architecture.
It's very hard to comprehend the blackest black in the world. I mean, you hear it, it makes sense, you think you can conceptualize it, but seeing it is something very, very, very different.
It's so black that it changes the dimensionality of an object. It's not a colour, it's the absence of colour. So it's what happens when you have no light reflected back to the viewer, you see nothing, so your brain paints it as black.
It might look like paint, but it's actually made up of microscopic carbon nanotubes, which are grown in a lab just outside of London.
It's made from individual carbon nanotubes, and those carbon nanotubes are like very, very long blades of grass. Now you imagine if you were a human walking around in grass 1,000 feet tall, how little light would get down to you. It's kind of like that, but on a very, very tiny scale.
It's pretty much like a black hole.
That's an interesting comparison because this material is helping scientists peer deeper into the heavens than ever before. Acting a bit like a lens hood for a camera, Vanto black basically prevents lens flares in powerful telescopes. Reducing that stray light allows us to see some of the faintest and most distant objects in the universe. So the closer we get to achieving absolute black, the more we are able to explore the blackness above. But space isn't the only frontier. Artists, designers, and musicians want to get their hands on Vanto black. Asif Khan is covering a building in Vanto black for the 2018 Olympics.
When people look at this building, they will see a sort of a schism in space. It'll be like you're looking into the night sky. And in fact, we're creating a kind of star field within this blackness. So it will look like the Milky Way, but you'll be seeing it in broad daylight.
The ability of Vanto black is to really make us think more about the light that we have access to. It's got the ability to make us realise what a precious resource it is.
Now, in forest of the polymer there comes a tree called Polymer Blend. A polymer blend, or polymer mixture, is a member of a class of materials analogous to metal alloys, in which at least two polymers are blended together to create a new material with different physical properties. So for a glance we are connecting with a video of polyurea coating.
From the top of this 45-meter drop tower, my friends from the How Ridiculous YouTube channel are about to release a watermelon.
Here we are.
In free fall for a full 3 seconds. The watermelon accelerates to over 100 kilometers per hour before smashing into the ground. The results are predictable, but this was just a control for the actual experiment. Another watermelon was sprayed with a polymer coating. We'll come back to what this is and how it works. But for now, let's see how the coated watermelon fares in the drop test.
That's insane. Oh, you're kidding me.
Instead of shattering, the watermelon bounces and remains intact. For the most part, anyway. With an axe, the How Ridiculous boys can't crack this shell.
How is it not? Ah! Oh, yes! Sure we can pull through that. Oh, look, it's actually... Oh! Look at the watermelon. It's intact. It's still a watermelon. Look at that. Oh, that's gross. That is amazing.
It is pretty amazing that the watermelon could survive an impact at over 100 kilometers per hour. So I went to find out more about the coating, called Linex.
It's a mess. The individual components are a mess. When it goes on as a big mess. You saw me wear a spray suit. It's a mess. But when you're done, you're really cool stuff.
Linex is made from 2 ingredients.
A and B. Inside of each of these is multiple things.
But the main component of A is diphenylmethane 4,4-diisocyanate, or MDI for short. It's very reactive due to these groups on the end.
B is the poly. So the simplest way I could explain is it's a plasticizer.
The main component of B is alpha-2-aminomethylethyl, omega-2-aminomethylethoxy, polyoxymethyl-1,2-ethanediol. Long name for a long chain molecule. In reality, it would be many times longer than this. Now I managed to convince Bryn to let me mix the 2 ingredients the old-fashioned way, with the stir stick.
And that's the A.
That's the A.
Wow.
I'm gonna dump A and B in here and you just mix them and see what happens.
All right.
Okay. Ready?
Yep.
All right. Go for it.
How quickly should they react?
They're reacting right now.
Whoa. Did you see that? That is crazy. And you can see there's almost like, I don't know, smoke or something coming
Well,
out there?
it's probably getting quite warm. I guess I could have got the thermometer out for you.
Whoa.
Can you feel the bottom? Tell me. You tell me.
Yeah, that's very hot. It's like the bottom of a hot... Ooh, very hot. cup of
Very
coffee.
hot.
Yeah.
What's happening here is the molecules of A and B are reacting to form long chains. Where they join, they form a urea group, so the substance is called a polyurea. The structure of these chains is responsible for the properties of the coating. So it's hard because it's made of a tangled mess of molecular threads, but flexible because these threads can be stretched out and then snapped back into place. Things you learn doing the reaction this way are that it's rapid, only taking seconds to react, and it's exothermic. A lot of heat is given off as these bonds form. But this ball of Linex isn't really useful for much, so how do you mix A and B to form an effective coating?
Put them really high pressure, force them together in a really small space, high temperature, high pressure, just ram them into each other. That essentially mixes them, and then they come out the end of the gun. So from the time they're separate components, they mix, out the gun, hit your target, fraction of a second. This is where the magic happens. Inside here. So you pull the trigger, out comes Linex.
We decided to Linex a piece of paper to see how strong the coating is.
As you can see, it came out as a hot, high-pressure liquid. Okay, now...
How hot is that? It's quite warm.
It's quite warm, and because that's an exothermic reaction. It comes out at 150, but it keeps getting hotter and hotter. You can probably rip it right now.
I could rip it?
Yeah, I think so. There you go. Okay.
All right.
Those two chemicals just keep kind of looking for each other, or looking for something, so to speak, until every last molecule's found a home or given up looking, and that could take a day or more. But there's plenty of opportunities to cross-link right now. So So that's what it's doing, and that's where all the heat's coming from. Right. So it's already dry. I'm not going to get any on me.
Yeah.
It's already cooling back down. So we've done the vast majority of curing and cross-linking.
Okay.
Yeah, we're getting there, right?
Yeah,
we're getting there.
It was harder.
It was harder. So now we'll wait till some of this heat goes away. We're probably getting a good amount of curing going on.
It is really tough to rip at this point.
It's strong stuff. Yeah, no. That tensile strength will get you.
That high tensile strength is the same reason the Line-X coated watermelon bounces.
That's insane.
As it hits the ground, the contents of the watermelon are squeezed out sideways. But the tangle of polyurea molecules pull together, preventing the rind of the watermelon from deforming too much and breaking apart. So the watermelon bounces instead of smashing. This type of coating is now used in the walls of the Pentagon, preventing exterior explosions from launching shrapnel into the building, the main cause of injury from explosions. And it's used in bulletproof vests to contain bullet fragments that could cause serious injury. All of this is pretty incredible for a substance invented as a truck bedliner.
Yeah.
Now, we are going to interact with smart polymers. Smart polymers, or stimuli-responsive polymers, are high-performance polymers that change according to the environment they are in. Such materials can be sensitive to a number of factors, such as temperature, humidity, pH, wavelength, or intensity of light, or an electrical or magnetic field, and can respond in various ways, like altering color or transparency, becoming conductive or permeable to water, or changing shape. Shape memory polymers. Usually, slight changes in the environment are sufficient to induce large changes in the properties of the polymers.